Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. This is the 30th lecture and this is the last lecture of the module 6 or the week 6, and this lecture topic is structural concept and application of dome in architecture. So, in this lecture we have following concepts that has to be covered. We will start with the definition and the historic examples. We will go for the support systems of the dome, how the dome can be supported, the structural concepts, types of the dome. We will talk about the geodesic dome and then some of the case studies we will see. The learning objective of the course will be we will outline the parts and the various types of the dome, and we will illustrate the structural actions of the dome and the application of the dome in the modern buildings also we will see through some case studies. So, what is a dome? Dome, as you all know, that is a shell, one type of shell, and that is a synclastic kind of a shell which is having a double curvature, and this is one of the simplest form of the synclastic shell. And as it is a synclastic shell, as you know, it is the Gaussian curvature is positive because both the curvature are of the same directions and the radius of curvature in the same directions, and they are positive, and it is used for the roof covering and for the ceiling. So, in the from the architecture point of view, it is actually look like a hollow the half of the sphere, which is a hemispheric kind of a thing, and dome are being extensively used in architecture since the classical European period to Islamic architecture. There are a lot of examples, and also the modern architecture also there are. So, initially, I mean, we will start with some of the examples of the dome, and you will see that yes, this is the first is almost 120 AD, Pantheon in Rome, which has a dome, and Saint Peter's Basilica, Vatican City in 1626, which is also a kind of a dome, and that has its all character present of the in the dome. And see, it is much more this Vatican City, this Saint Peter's Basilica is a much more dome that is I mean, in the history, I mean, this particular type of the dome is repeated in various forms in the various part of the world. So, I can say this is a very mature, this all in 1626 itself it has been matured in one of the strong component in the architecture. Then you Istanbul, that is kind of a flat kind of a dome, which is in Hagia Sophia, which is Santa Sofia is also known as. There are multiple domes, and the central dome is a bit of flat. The another one which is very famous and very we must proud to have those kind of a structure in our country is the Taj Mahal, the great dome, onion dome. This is a Islamic dome. The Hagia Sophia is a Byzantine dome, the earlier one or the Roman dome, and this Taj Mahal dome is a onion dome, which is a Islamic dome, and this also has its own character and own proportions and nature. In other historical domes in the Islamic history, you can see some the Bijapur, the Gol Gumbaj, that is another very perfect hemispherical dome example of that. And in the modern times in India, Matri Mandir, Auroville, if you have gone through, you have seen there is a perfect circular kind of a dome has created in house a particular meditation hall in 2008. So, there are ample of types, I mean the examples available in the history and the modern architecture also. So, let us now discuss about some of the support system of the dome. In the support system of the dome, if you see, this is the in the right hand side, left hand side, the figure is for a dome which is classical dome, you may say. But even if it is a classical dome, there are some character which impart some kind of a visual or the architectural element in it, and some of the part which definitely has kind of a some functional character. So, the topmost part of the dome is called cupola, which is a mostly as the architectural the feature or the element, but also it will take care of some kind of a light through it, I mean the daylight also. Because if you see this classical period, then there was no electricity, and those days there are they have to I mean the design with the daylight also. So, and below that, just in between the main dome and the cupola, there is a lantern is placed in between, and that is also designed for natural ventilations and for the lights. And then start that particular the dome, the actual dominating the visual element in that particular the structure, the dome, which terminated in the drum, terminated in the drum, and drum has lot of openings to take care of the ventilations and all. But there is another reason for giving this this drum is because the dome is having a circular in character, and that has to be actually support the thrust and the vertical whatever reactions to a wall, finally to a wall, and wall definitely give it to the foundation. So, you need to have a kind of a transition element, structural transition elements also. So, they have used that particular drum, a particular drum just below the dome and just above the supporting wall. And when you do that, a circular dome sometimes directly stay on the peripheral walls, and the peripheral walls either it may be octagonal or maybe it is square. So, how this particular dome, the hemispherical dome, is going to suddenly become the square in wall in shape? It done by two ways. One is called the pendentive. The pendentive are those are the pendentive. It is a smooth and gradual filling of hemispherical dome over a square or rectangular base. So, finally, I have a square kind of a the room or whatever the wall. So, and this is a dome which this portion is touches with this portion. This the central portion of the dome is just above this portion. So, it is tangential, but if you see the footprint, it is something like this, the other part of the dome. So, gradually it has been smoothening and filling and to come down to this particular corner points also. So, that this type of the arrangement is called the pendentive, which is if you have seen notice some of the domes in some churches or maybe some kind of a hall, you definitely there are pendentives. Or instead of pendentives, we can go with the squinch system also. This is the second system. So, either pendentive or maybe the squinch, any one of them has to be used to transfer that load. Here there maybe you can go with this kind of the drum. This is the dome and this is the drum, and it is also a gradual change of the filling of the square to the square base for the hemispherical dome also, but it will be definitely done in the internal side. To this particular change phenomena is come in this internal side. This is the internal side gradual that filling up or the smoothening is occur from dome circular dome to the this peripheral square walls, and to that will receive the dome in that way. And after that, sometimes what we do is that there are arches which are crossing with each other in the same axis line, and it create a vault. The ground vault is something like that when there are two cylindrical arch, perfectly cylindrical arch. You see, this is perfectly cylindrical arch are actually moves like this and another like this. So, there are four such ridged or the ridge will create, and that will create a ground vault, and it can be of ribbed vault also. In case of the ribbed vault, you see this particular is a hemispherical arch, or this is a barrel vault. But here it is not a barrel vault, it is it is a pointed arch and it is a pointed vault kind of a pointed shell kind of a thing, and this is another similar in a orthogonal way on 90-degree orientation, changes the orientation. It will also have the 4 such ridges, another in that side, but it will also it's the total overall dimensions, overall the flying of those ridges and all will be definitely going to change with respect to the growing vault. This is called the rib vault. So, instead of the pointed arch, it can be a parabolic, it can be a kind of a very flat segmental. So, you will get different cross sections in nature and different type of the ridges, and that can be seen through. And only one thing you have to take care in case of a vault, that this, if it is segmental, the dimension of it, the rise and the span should be matched with this rise and the rise of that also. Sometimes it is also happened that in case of the, it can have a longer one and it can have a smaller one also. So, that also can be. So, there may be a height matching, or that may be sometimes the span matching has to be there to create a kind of a the vault. And this is the cross section of the Hagia Sophia, that is the Istanbul the mosque, and we will study that one from one interesting thing we have to study, that is in the central portion dome, which because of the arc or the curvilinear in nature, it will provide some kind of a thrust, as you all understand now. And as and when it is giving some kind of a thrust, this thrust is actually going to taken care of by like the stepwise formation, and some of course definitely going to give some kind of a reactions over here by some the flying buttresses created by the hub dome. These are the hub domes. So, if you see, if you go to the Istanbul and visit this particular the World Heritage Site, you will definitely see that particular there are the hub domes are there. And that is taking care of the particular supports also, and basic principles of the supporting systems of the flat Byzantine dome is something like that. They created the hub domes in the sides to take care of the load, and also it will the cylindrical wall, which is the surrounding that particular flat dome, which pendentives, they have taken care of the vertical load downward. So, a series of arrangements. So, the formation of those time, the churches and the mosque are basically based on some structural principles, or even there are some need of the pendentive, sorry, the flying buttresses. So, in case of the Gothic arch, it is just a flying buttresses which are taking care of the thrust, but here that flying buttresses are taken care of by the half domes, a further improvisation. If you see the Rashtrapati Bhavan, New Delhi, our Rashtrapati Bhavan, New Delhi has 2 domes, one which is which we can see from outside, and one it is invisible from outside. Of course, if you go to the Darbar Hall is this. Darbar Hall, you can see from that is the ceiling of that particular dome. Now, these two, if you see the plan, you see this is the footprint of the dome, which is this, are giving some kind of a thrust, and then that has neutralized by the side domes 4 such important, and there are some small I mean the structural footprint here also. So, those associated structural footprints are actually taking care of your those neutralizing your the horizontal thrust or the line of thrust actions also. So, those are actually created in those days, and this is the I mean the one of the famous structure in the Lutyens, Delhi, and you can see that particular how interestingly that particular structure has been built in a formation where there are supporting small domes and small cupolas addressing the beauty of the overall site or precincts, and but this also taken care of by the some of the structural load to for the grounding purpose also. So, let us go to the some of the the structural concept of the dome. So, if you see the dome, there are lateral lines and the longitudinal lines, latitude and the longitude will be called. In the longitude point of view, which is this, the longitudes are this, they are having the meridian lines called meridian lines, or they are having some kind of the stresses are there in the meridian stresses. The latitude of the radial lines, which is full circle, and those meridians are of half circle, and full circles are of radial lines, they are actually taken care of some hoop stress. So, in a dome there are meridian and this, so there are some two type of stresses will occur in that particular junction. Any such point you take, there are two such meridian and the latitude and the longitude, meridian and hoop will be there. So, if there is a dome which is a will be under some kind of a load also, suppose this is some kind of a load, if you put some kind, or its self weight or the load. So, because of the self weight of the load, what happened is that the top portion is sink down and the bottom portion is go out. Something like if you just press a balloon, what will going to happen? The top portion will sink down and the bottom portion will go inflated much more, and it will bulge out. So, it will going to happen here also. See, it will going to, the green color is the final color, final after the loading has been done, it is sink down and that. So, from this phenomena we can understand that this particular hoop has a clear cut different nature. This hoop are these blue color arrows are the hoop, and this upper portion, if you see, the hoop circles are going to contracted because it is under compression, it is sinking, and so as the diameters or the whatever the perimeters are sinking, the hoop stress is compression in the top portion, upper hoop. Whereas in the bottom portion, what happened? Bottom portion is bulging out. That means it has tried to expand its diameter. So, that means it is under tension, and the hoops in the loop it occur in the lower hoop cycle. So, this is going to under tension and this is going to under compression. So, there is somewhere it is going to have 0, and then there is a tension hoops and there are compressive hoop stresses also. But meridian stresses are always under compression. See the red arrows, these are always under compressions, and this blue squares whatever I have drawn is some element, small very delta element in a particular the dome surface. So, now if you see the formula, so the derivation of the formula is not in our scope. So, hoop stress is given by this formula, where this W is the loading intensity, how much is the load, and the R is the radius, this is the R, and the angle is measured from the top to bottom or from this point to this onwards. So, if you find out any angle, want to find out the stresses in this angle, you have to find out this, not this. So, the hoop stresses are given WR into cos square theta plus cos theta minus 1 by 1 plus cos square theta, whereas the meridian stresses given by WR by 1 plus cos theta. So, it has, if you see, I will go to the next, and if you see, there is a zone 1 and zone 2. In the zone 1, these portions hoops are compressive, and after the 50 degree, almost after 50 degree, this portion 50 to 90 degree, this portion is zone 2 where hoop are of tensile. So, we have to very careful, we have to see that how we are going to design this portion of this portion and this portion of the 50 degree, below 50 degree portion of the dome, because those portions the tensile stress comes, and as you know, the concrete is very weak in tension, or any kind of brittle materials is very weak in tension. If you go for a brick corbelled dome also, those portions has to be taken into account, the thickness has to be increased also, or maybe some kind of reinforcement has to be provided, or in case of the concrete we have to actually design that particular portion with the sufficient number of tensile reinforcement also. So, we have to see that, and we have to see how can I find out this 50 degrees also. It is very simple. You can do one thing, you can just start calculating the theta values of, give 0 degree, 10 degree, 20 degree like that, and find out this particular coefficient, and as and when this particular coefficient is negative, it is compressive, it is tensile, and if it is positive, then it is compressive. But you see the meridian stress is 1 upon 1 plus cos theta. Cos theta is 0 degree is 1, cos theta is 1, and for 90 degree it is 0. So, it is fly from 1 to 0, all positive. So, 1 plus whatever, it is always going to be positive. But this, there is a chance it is a positive and sometimes it is negative, and when it is negative, then it is a tension, and when it is positive, then it is compression. So, let us see if I do multiple various degrees, and if you try to plot a graph, you will see this blue color one is your hoop is changing the sign. This is 0, so this is positive, this is negative, changing its sign at around 51 degree or so. So, that means till 50 degree, it is positive, that means it is compression, and after the 50 degree, this is negative, all negative, because this is, so this coefficient is negative, so this is negative, so this portion is come under the tension. But if you see the meridian stress, which is in the saffron color, so it is starts from here and it goes almost up to 1.5 to 0.1, and for total span of 0 to 90 degrees. So, there is no question of any negativity in the negative things in the meridian. So, there is meridian is almost completely under compression source, but hoop changes. Now, let us go to the type of the dome. There are various types, and various types are defined in a various way. The first and simplest dome is called the radial dome. So, I am talking about this dome as if you are going with a structural trusses or some structural members and then going to cover with some kind of a covering element. So, it has rings and radials. So, there are rings and there are radials. So, these are the member or something like rings, and the radials are the two typical members, and in the rings and radials are of placing in the different height and the different diameter, and the radials are of same length or so. Now, this is called the radial domes, and it is called laminae also sometimes, and also there are some kind of a spherical dome, which is there are the rings, radials, and one diagonal. See, the change is if you just put one diagonal, then it will from the radial dome it will go to the spherical dome, and then next is we go with the lattice dome. The lattice dome are actually there is a small problem in this is called ribbed dome, not lamina. This is ribbed dome. I did a mistake, and this is called okay. So, the lattice dome or the laminar dome, that is there is rings, but there is no radials, and the two diagonals are there. There are rings like this, and there are two such radials. So, that will create a kind of the lattice dome, and finally the geodesic dome. The geodesic dome is very interesting and very efficient also from the structural point of view. So, whole surface of the hemisphere is divided into equilateral spherical triangles. It is not the equilateral Euclidean triangle, it is a spherical triangle. So, those spherical triangles are actually covered all over. It is something like if you just develop a kind of a hemispherical things by pieces of some flexible pieces of some clothes or something like that. So, that is the geodesic dome. So, there are again examples. The example of the geodesic dome, the US Pavilion at Expo 67, which was done by the architect Minister Fleur. So, that is one of the example of that, and there are some example of the geodesic dome has been constructed in our department of architecture of and regional planning, IIT Kharagpur. Students has done under one of the lab. That our material testing lab, that was actually they have designed every time they are designing some of the things, some of the construction and some of the interesting things in our backyard. So you see, this is the dome that created by the spherical triangles, and the geodesic dome, so this is one of those unit of triangle, and they have actually, this is a fix, how they are fixed with that some connections and all with the bolt also. So now this geodesic dome has some kind of the frequency also. It is very interesting to know that what is the frequency. So if you see a particular isosahedron, so that is a particular object, a 3D, which has 20 triangles, 20 such triangles. You can count those 20 triangles. And these triangles are, if you take one such triangle, you can further divide that triangle into further pieces by dividing this into equal 2 or maybe 3 or maybe 1, 2, 3, 4 or maybe 5, 6 like that. So it can actually divide those maybe in 3 or whatever. So like that you can divide those. So by if you go further divisions, your smoothness of this isosahedron will be much more, and gradually from this it will go to a sphere. It will go to a sphere. So if you go with only the one unit of isosahedron, then it is the one frequency. But if you go with the divide that by 2, and that same space is now divided by further 2, and you are smoothing that particular the triangular part, it is 2 frequency. Now if you divide that same triangle by 3 such equal way, and you can create that surface furthermore smoother, then it is your 3 frequency, your third frequency kind of thing. So that is the frequency. So we start with the first frequency, which is very much equal to your isosahedron, and from there we take one after another the unit wise we increase the further the divisions of that triangle, and then we go for the further this thing. So onion dome, again some variations let us discuss regarding the onion dome. Onion domes are widely used in the Islamic architecture. So in that, if you see, if you have a rotation axis like this, and this is the generator, and if the generator is perfectly half circle or the quarter of a circle, sorry, and these tangents are of these are 2 tangents, or the angle is suppose 0 degree, then it will give you a perfect circular or the hemispherical dome. But if you have the tangent like this, having some angle and having some angle, and by virtue of the variation of the angle, this is smaller, this is wider, this is all, both are equal, and here you see this is, both are smaller. So by virtue of this, changing the angles, tangent angles also, we can actually create different shape, different type of shape. So it is basically because of this tangent and all, how much it is, this tangent is moving. This is moving very small, but this is a very wide. So how much angle it is moving, from that point of view, if you change that, you can create a lot of type of dome, and that can be visually appealing, and that has been used in the Islamic architecture in an extensive way. Let us go to some kind of a case study. This is another great master architect and also a engineer, Felix Candela, a Mexican architect who has done some of the work in the shell structure and all those in the Mexico. We will discuss some of the works in our next week also, in the plate and the folded plate. So it is a factory in Mexico. It has 3 such units, 1, 2 and 3. Of course it is having, if you see, it is having 6 actually. This is the same unit or so. The 6 units are of having high paraboloid, and would create a going kind of a vault. This is hyperabolic paraboloid, and this create a kind of a vault. One module is a vault, and this vault is having 4 centimeter thick, that RCC, and it has been having taken care of the almost 26 meter span and square plan with 2.5 meter is overhang with each other. So, this much is the 2.5 meter overhang of each other. So, from the plan. So, this particular vault are taken care of, and then the further interesting thing is that if you see this particular vault, you will see there is when there is 2 vaults are, I mean the side by side vault intersect, that particular intersect has the edge beam which is like this, and this edge beam are actually filled with glazing, which allow a lot of ample of light. So, there are a lot of cross sections, and those cross sections are creating the light, and of course, there are these portions are also glazing. Another interesting thing is that if you see how the finally it is going to support this, it's supported by some through the shell, but not a continuous support. It is creating some kind of an inclined kind of a support by the virtue of 2 system, 2 kind of a stiffener and the inclined column, and that create this 4 point support, and one is in this point. So, in the industry, as you know, you need a long span areas for movement of the trolleys and maybe some kind of the equipment, goods and all. So, as much as we go for the reduction of the columns, reduction of the footprint of the structural footprint. So, it could have been a nice way to take care of the structural system such a way that the 26 by 26 meter of the span is almost freestanding and no obstruction at all, which is definitely we welcome in the industrial architecture. And in industrial architecture, if you can create this kind of the marvelous visual beauties by virtue of undulated shells and all, that's fantastic. So, we have some kind of a idea. Suppose we have a rib slab or rib dome. So, we have the rings and all. Sometimes we may this laterals we may cut it over there, truncated over here. So, that can be also done. Sometimes we may have some kind of a dome, and we can cut the dome something like that, or maybe then we can split the dome in like this, and then we have some typical kind of a situation where we can have play with the different formations or so. This is another example of what I have just now explained. If you see a dome, and this is the plan view, and if you just cut the dome, sometimes we may cut the dome into 2 pieces. So, in that case, if you cut the dome into 2 pieces, so suppose this is the dome, and if you can cut the dome into 2 pieces, so something like that will going to create on one dome half dome, and another dome is higher. So, you can play with the different formations. You have in the elevation something like this, something like this, some building elevations like that. So, it will be create a lot of story in your form. So, this is the Indira Gandhi Rashtriya Manav Sangrahalaya in Bhopal, where we can have those kind of a cut domes, the half cut domes also, and this is another kind of a dome, very interesting, and it will create a allow the lights to be in, the daylight to be in inside this particular museum, which is a wonderful museum, and the structural arrangement is also very wonderful. And those are the some of the case studies. I think this is the last case study what we have discussed. These are the reference. In conclusion, we must say that the dome is one of the simplest form of the double curvature shell. The hoop and meridian stresses are the predominant in the dome, and domes are classified into mainly 4 types, and there may be a huge application in the dome. The next lecture will be on the next week in the module 7, week 7, where in the 5 lectures we will discuss about the tensile and the plate structure. I have some homework for you. The first one is again a sketch kind of a thing. You sketch a dome over a square hall and name the various parts. So, that is just for your understanding and all. And second one is a very bit of mathematical. Then hemispherical dome of 12 meter of diameter, and that is under 10 kilonewton per meter square of the loading. So, that is your 6 meter is your R, and this is your W. So, find the hoop and meridian stresses at these three angles, 0 degree, 45 degree and 90 degree. We have already the formulas are given to you. We can just put the values of W and R and theta and calculate the stress. Thank you very much for listening, and we will go to the next week. Thank you.